Let's hear it for our speaker. Thank you very much for coming. Hi all, thank you guys. Today, we talk about PT. My name is Gleb Kumychov. I'm the lead specialist of data science ML department. Let me share a few facts that we encountered along the lines. Three main sections. Introduction, let's see what this product is all about, how ML can help you. Then we'll take a deep dive into the specific implementation. And finally, we'll talk about implementation and plans for the future. Let's get started with a pretty simplistic, popular example. Details do not matter that much. Let's imagine we have an employee who receives a phishing email in their mailbox. They open this email and there is malware contained in it that loads payload from a server owned by attackers. Then routine hacker activity starts. Some reconnaissance, then they reach the domain control, they increase the privileges. Finally, they get to a service which gets encrypted. Then they ask for ransom. If this is what an SOC employee sees on the screen, they will feel concerned in the middle, and then we'll take action. And we are working on Max Patrol 02, identify and prevent. We will focus on the first segment, identification. How does O2 work? It's a meta product that takes data from SIEM, breaking it down into resources and relations. It contains more information, it's more complex, but of the overall context is this. Let's take a look at real-life data, real-life attack chains. Let me make a disclaimer here. There will be duplicate terms. I will refer to chains and graphs. Chains and graphs mean the same thing. And resource and vertices are synonymous. These are commonly used synonyms. So chains are graphs and the vertices are resources. Resources are anything we can interact with. It may be a file, a process, an email, whatever. Any object interaction can occur with. They have a set of attributes, and we'll tackle this later. Resources are interconnected. The connections may be of different types, multiple connections between resources. This is all based on raw events that come from SIEM. If need be, we can get back to the original events, pulling dozens of attribute fields and map these, if needed, based on our data for the data enrichment. What is the place of ML? In a perfect world, how does a system like that is supposed to work? It normally works fully automatically. An SOC operator only receives relevant incidents worthy of their attention and time, and everything works without any errors and perfectly. As you might have guessed, in real life, it's far from that. It does work quite well, but still you've got FPs, false positives. They do occur. A number of issues may occur. Valid activity may be mixed in. It needs to be identified and isolated. It might be difficult to figure out how a chain works. And ML seems to be able to represent a bridge connecting the present state and a perfect world where everything is working fine. It would be easier to share expertise to a product using data. Challenges and difficulties faced when working with machine learning algorithms in this context. In the first place, or rather not in the first place, but rather this is not of utmost difficulty. The data is various, heterogeneous. We can deal with that. more relevant issues, a huge deficit of data. As it is usually the case, we have lots of false positives and a very low amount of actual attacks. This causes a huge class imbalances. We have lots of chains and datasets, annotations, and there is no sufficient amount. Hence the question, how do you approach that? The matter is that one of the key objectives which may be useful is building versatile embeddings, helping us resolve a number of downstream tasks, including classification. We're interested in search, rating, something that will help us in day-to-day routines. In the absence of markup, how do we approach that? This is the question. We decided that we should solve a problem that does not require any markup, that will help us come a step closer to embeddings. And the search task is in line with these criteria. What makes it interesting per se? If we get a search feature in the product, when investigating events, we'll be able to see how similar incidents were investigated in the past. There is a distance we can trust. We can use it to automatic application of such verdicts to verify legitimate and illegitimate activities. This can be used for auto-propagation of verdicts. We can perform a set of additional tasks that helps us coming a step closer to building embeddings and additional features. Once we got this out of the way, once we got this goal setting out of the way, let's now proceed with the details and the way we solve this task. Let's take a deep dive in what we are looking for, the approaches we used, what worked out, what didn't, and results. There is a very interesting point at the very onset of this routine. This may feel trivial. What are we looking for? When we started dealing with experts from the SOC and colleagues, well, there are various definitions. Some chains may be similar if they have a similar set of techniques and tactics. Is it valid? Yes, it is. We can say that they may have similar activity. Is it valid? Yes, indeed. No problem with that. The same applies to the presence of the same host and resources. There are multiple dimensions. There is no single ruler we can apply to measure that. So how do we apply this to ML? The trivial approach would emerge if we could ask for a list of such events, applying some rule bases, and proceed with this. But we wanted to have something which is more unified. Therefore, we have this hypothesis. If similar ones are considered those that have chains that have a similar set of resources in a similar context. And this must be verifiable in experiments. If experts, based on their reasoning, brought chains they consider to be similar, and we've identified those through our methodology, it means that we have resolved the task at hand. We can take a look from the other standpoint. Similarity applies to similar resources in a similar context. This brings us to the conclusion that it is pretty similar to the concept of graph neural networks. There are neighboring nodes defined by embeddings. If we can aggregate the neighboring embeddings to the same vertex, we will take into account the context. Every node would be coded based on the neighboring ones. And in a perfect world, we'll be able to resolve the task at hand. This is one of the approaches. Graph convolutions are included. What does resources look like? Resources are described by various text fields. These may be category, attributes in various languages, in Russian or in English. We'll discuss this in detail. We need to represent this somehow and encode this somehow. All right.
Нам добраться до финального представления цепочек и перейти уже
to get to the final representation,
как их закодировать.
We need to somehow encode the nodes, convert this into a graph, aggregate embeddings, and hopefully we'll get the desired outcome. The main idea is that we keep the chain the way it is, we move away from heterogeneous elements. We encode them as embeddings, and we used graph-based neural networks for encoding purposes. This helps us to get to a versatile pipeline. Should any data field change in the future, should their contents change in the future, we have a versatile encoder. We'll just plow through these without breaking the pipeline. What is missing is a text encoder which would be versatile for encoding various text attributes. Hence, the following objective. Find a text encoder. The data to be encoded is heterogeneous. It may be simple as a file or a path to a file or process. The data might be in Russian or in mixed languages. It can be anything. So we would love to get an encoder out of the box and start using it. We had no validation, I remind you, and we were unable to assess the quality of solutions. We needed to pick a text encoder. Well, we'd love to have validation. We'd take a look at the metrics. Okay, we love this one, we pick this one. Unfortunately, back then we didn't have an opportunity like that, and we decided that we could build a micro benchmark based on our data to be used for a comparison of various open source encoders and to pick a good option. How to build such a micro benchmark? We'll take the data that can be put together, that is data belonging to the same category. We can take a look at the clusterization, we can take a look at the classification, we can find the closest category and get specific values, filtering out encoders that do not work for us. This is going to be a useful table where we compare various encoders from Hugging Face. You can look them up based on their names. Apart from the obvious parameters and the definition of embeddings, we look at the tokenizer. Why is this important? Why is this overlooked quite often? Quite importantly, we have the amount of unknown tokens. If we have lots of unknown tokens, tokenizers will not perform quite well in our domain. The number of tokens is also useful because it is an indirect way to assess how well a tokenizer works with our domain. Domain-specific ones will be broken down in smaller chunks which are less sensible. We also keep track of encoding to see whether tokenizers work with Cyrillic because we have mixed languages. Quantity. We rely on a small data set. This is metrics pertaining to classification, clusterization. Then we have a column that says ratio, how well this hits this domain. If very close, it doesn't work quite well for us. So we summed up all the metrics, the higher the better. Higher is better, and we pre-selected several models to further work on. And we got pretty amusing results. Before we take a look at this, let's take a look at the differences. We'll take a look at the top-performing model in terms of metrics, and another one which is not a top-performing one. Simple things like Windows, Host, Linux, they represent tokenizer pretty much the same way. If we take a look at other things, for instance, someone was listening to Yandex Music. It's not a bad practice, I do this myself. One of the models represented as Yandex Music, and all these terms were not separated. The other model does not understand that. It breaks it down in different tokens. And the hypothesis is that breaking down terms like that prevent you from ensuring a high-quality representation semantically. When we reach, next slide hopefully, when we reach Cyrillics, we can see that one of the models, it's not a surprise, but this is important, it just fails to process Cyrillics. So the model breaks. If we take a look at the visual representation, you can see that in one case it's pretty condensed. In the other case, it is spread out. If we take a look at classification, if the diagonal is red, it's okay. If we have lots of red segments all around, it's bad. In one model, it's pretty condensed. The same entities are close together. And the opposite case, these are spread out. When we got data sets subsequently, we were able to measure real-life metrics and take a step back. These proxy assessments, to which extent do they represent real dataset metrics? It turned out that the correlation was really good. The rating of models matched on downstream metrics and what we assess on a small, simplistic data set. And something that I failed to realize completely as I was preparing this PowerPoint. Take a look at the huge difference between metrics. It's almost 2 times difference between the edge cases. When you go to Hugging Face, the domain seems to be yours, the modern bird is or secure bird. You expect it to perform quite well, but the metrics turn out to be 2 times lower compared to one which fits our model, our domain. We could have started with modern bird, running experiments for 2 months, getting a 30% growth, and being happy about how well we grew. But we could have just selected a better model, closing the gap within a single day. If you don't have a specific benchmark within a given domain, try to build a solution based on specific values rather than relying on your intuition. Many of you might think, why didn't we fine-tune our model? The answer is short and simple. Back then, we didn't have a data set to compare to fine-tune models with. When we got it, we filled the itch to do some fine-tuning. Summary: if the models were trained with masking, MLM, their fine-tuning helped to increase the metrics, in the best case, by 10%. If we used other loss cases, the fine-tuning would just break it down completely. It turns out that the best fine-tuned is still performing less efficiently than a correctly selected model from the outset. We selected encoder we can work with. New configuration, we quickly select a subset of fields we can work with further. We can play around with various configurations. We code text attributes and we get a graph as an output, which has attributes for vertices and ribs. We can then use an ML. The final ingredient which is missing is some kind of validation. Finally, we got it. In the process of solving this task, we built jointly with our colleagues a validation dataset. Building this dataset is like finding a needle in a haystack. Finding similar chains from scratch in a large database without any tools, that was a pretty challenging task. So the data set was enriched gradually. When we got solutions, we ran them on our database, thus selecting candidates. This helped us speed up the process. We check how metrics settle down at around 90 samples. And we get a pretty various but quite representative data sets of grouped up chains. This is for us to track validation. By validation, we mean retrieval metrics. If we find some relevant chains, that's great. We put it down as 1. If not, it counts as a 0. We refer to recalls and the MRR metric, mean reciprocal rank. How quickly the first relevant result appears in the output. We've set it up, we have a model, we have representation, we have validation, we can run experiments. We felt really enthusiastic about that, lots of approaches. It's been a challenge. We got some pretty good metrics, but not quite inspiring ones. And we would strive for more. At that point, it was not a block, it was not a blocker, but we couldn't exceed the metrics in the slide. And we got an idea. We can approach this from another side. And this is what we did. Let's approach it from the other side. Let's think out of the box. Let's use the following perspective. We have two chains, two graphs that we need to compare with each other. We can still rely on classical algorithms, one of which is a matching. We can compare the vertices of this graph, finding the best match, and we see what matches between these two graphs, and we can measure the distances between two chains. Is it an option? Yes, it is. So we have a certain distance function we can define. One of the components will be responsible for how well the vertices match between two graphs and how they differ in size. It's important to separate these two aspects. This outputs a distance function, helping us to come up with a better solution compared to the previous approach. What is missing? Just we need to determine the distance function, and then we carry on. We need to pick a certain distance function. This is quite a particular aspect which is often overlooked. You can choose a random function, which we did. We could choose a function, but that would become a matrix. So, there are several properties. What is the trade-off? We want to perform search and clusterization. We have lots of theory guarantees, hoping that it will perform better. This gives room for optimization of search. If it's a random function, we don't have such guarantees. So we get a trade-off, which could be resolved by taking a look at the practice, finding out what works better. As we ran experiments, we went for this function. The first component compares how well various vertices match up. The second analyzes the differences of graphs. We got an idea. All right, we are solving a pretty classical task. If we move away from the concept, probably the literature offers quite a lot to rely on. The latest articles were published last year. These are the functions that help us compare a set of points. This comes from the multi-object tracking for radar data. Why not to use it? Because this is exactly what we need. For such functions, we have all the mathematical proofs that confirm that this is indeed a reliable matrix. We got very pumped and inspired. Unfortunately, all the data, we tried processing with such metrics, they turn out to be of poorer quality compared to custom metrics. This is why we proceeded with this one. I assume that we will have further configuration, so we'll keep track of the status, and please do not overlook this function. We ended up having this pipeline. We have some training where we encode an input chain as a graph. So we train the model to mask several ribs. The model is supposed to find out which ribs are fake and which are the real ones. It doesn't require any human markup. We can rely on lots of data without annotation. inference, we got two options. One is to aggregate the final embedding, comparing two embeddings with any known distance. And the other option we have as an intermediate step. We can compare through matching one graph and another, and hopefully get a better result. What do we end up having as a result? This approach significantly improves metrics. With this fine-grained comparison, where we match up chains, the metrics turn out to be much better. Well, it's easy to see intuitively. Speaking of embedding, we have a very condensed idea of that. When we talk about detailed matching, it's all in front of us, which helps us better match up. So there is a productivity trade-off, because such matching is pretty expensive in terms of procedures. This leads us to think that, okay, we've got an approach that yields results. Not perfect, but still. And we have a better approach. Can we combine these two approaches with better metrics? Can we somehow relay the signal from the classical one to an ML model? There is an obvious answer. If we take a look at the inference map, this is rather not an inference map, but a training map. We can add a loss that will help us relay or forward this information as a target. In the process of training, we generate markup through a classic algorithm. This markup notation relays this data. And what is beautiful about this, that this matching function can be anything. It doesn't have to be differentiated. We don't have to run gradients through this. We generate markup annotation on the fly. And as we expected, and that was the actual outcome, helped us to somewhat improve the result. The addition of such a loss in the final embeddings, this results in better quality. Through this algorithm-based supervision, we pull out more quality information. The final embedding is of better quality. When we run comparisons by matching, it might have some fluctuations. It may go up and down. We would love to have one without trade-offs. Can we make this happen? Yes, we can. We use cosine differences.
Это позволило еще накинуть в метриках и практически везде.
We can use coarse and fine-grained modes. The difference is of 1/10. And we get the best results along this way. With pretty good metrics, we move on. Before we proceed with implementation and launches, we'll talk a few other useful properties for such solutions. First, capacity for interpretation. In this slide, you see one of the demos we ran for visualization when debugging a solution. On the right-hand side, you can see a comparison between various resources. And what makes it beautiful is that we can see what is the basis for a model deciding that specific chains are similar, which chunks it compares with which score, the final impact on the end solution verdict. This helps to boost credibility for an algorithm and generate additional ideas and identify bugs in such an implementation. Quite graphically, we can see what happens under the hood and influence that. This is one of the ideas that we got, and this is one of the interesting solutions. This is masking. Say we compare two chains, we made a matrix of distances, we find the best optimal mapping. But we can roll back to the raw data, remembering which vertex corresponds to which resource. Vertex 3 is process, and vertex 1 of graph is a host. And we see that files and processes match up with each other. Files and hosts match up. It might be an undesirable property because it would be quite incorrect that we have such a matching occurring. But if the score is high and if the total distance is significant, that may be an undesirable effect. We get an additional opportunity. We can relay expert knowledge in the following way. We can build a matrix of weights. A file of host cannot be matched. Matching a file with the process is bad, but not that bad. If we build this matrix just once, we can always multiply our initial one by the matrix of weights, thus banning all the matching between different types of resources. It doesn't require any further algorithms. It will work in the same way, but everything is going to be blocked, resulting in imperfect matching. This is a beautiful feature which occurs natively. Another interesting point. If you deal with graph-based neural networks, you might have the following question. Initially, we train the model to reinstate ribs. Some say that it cannot be applied to other tasks, and there is such a concern. Indeed, I would like to test it somehow. Can we actually apply these embeddings to other tasks?
По количеству датасетов, на которых мы могли это покрутить, пока что мы над этим работаем, но один из датасетов, который был доступен, это датасет.
We are working on expanding this, but one of the available datasets contained real attacks and actually some false positives. False positives that have high scores, so they do look like positives. The dataset itself is not colossal, so I won't say, you really need to introduce it in your production environment right away, but still we find the results to be quite promising. So for this dataset, we took embeddings from the previous stage, and we attached to this embedding some pretty simple models with, pre-scored classifications in them. Now, since the models are pretty simple, it's a way for us to show the quality of the embeddings and how much information they can convey. And I think the results are pretty good, even if I say so myself. Now, I've mentioned already that the dataset itself is relatively small. And let me stress here that the embeddings we use here come primarily from false events. So in the initial dataset, in the unsupervised data, so were in fact no real attacks whatsoever. In further training, the models actually did a pretty good job. So what's also pretty curious about it is that the additional LOS that we used, it also served to increase the quality of embedding in some scenarios. So this way, even without human annotation, using some classic algorithms, we can actually make sure that we bring more useful information in the midst of the embeddings. And I think that this way we can actually get a much better embeddings that would be capable of addressing pretty much any downstream thing we may have. Now, let me tell you about some deployments. We are running a pilot right now, but something I can already tell you. So there is no rocket science, in fact, here. The idea is like this. We're doing all our computations in the background, and it's just, the O2 that, returns responses to us. There is a scheduler, and, there is a queue, so workers get stuff from the queue. And once we get a request, we return a response with no latency. To UI, this one looks like. So in this window, you should be able to see the top 5, for example, but it's configurable. And this interpretability feature that shows what we compare it to what and why such a decision or some other decision was made. So it shows, this resource comparison with different scores. So why do we believe that this one is actually close to the target that we have, and why? Now, what's good about this? Effectively, we have here a single method that runs on embeddings, runs pretty fast. At the same time, we've got another way of doing it, which is taking much longer, but its performance is much better at the same time. So it looks like a pretty practical trade-off between the two here. And this is not entirely incorrect. In fact, we can use this fast method to select candidates and then invoke the slower process. So this is what it looks like on a graph.
общий
you will see here
того, какой процент
the
датасета мы
overall
берем
recall
в первый stage в кандидата.
depending on the percentage of the data set that we use for the first stage for the candidate selection.
Друг от друга цепочки мы хотим искать.
Obviously, the results will depend on the distance.
То для того, чтобы гарантировать
Like if we want to have the distance threshold of 0.3, we can only do calculation of 20% of the whole data set for stage 1. And then, we can drill deeper with the slower method. But if we are looking for more distant chains, you will have obviously very different figures.
Он квадратичен по объему цепочек, которые мы пересчитываем, поэтому если мы, например, берем только 20% в качестве
So if we go, say, for 20%,
то мы сокращаем
in the first stage, we are effectively reducing the amount of computation by a factor of 25 in the second stage. So every organization is invited to find their own sweet spot in this respect. But remember, it's a quadratic function.
Скажем, что на самом деле здесь есть еще одна
I should also stress here that there is another interesting option here, something that is not really up and running at the moment, for reasons I've already explained. But initially, the metrics were not as good, and had they been very similar, there would have been an additional option. We could have used a cover tree data structure that would have significantly helped us in terms of pruning the search space, thanks to triangle inequality, while at the same time maintaining a very good recall level. So I believe this is how we can actually find the optimum spot here, where we can guarantee 100% recall, while making the computations themselves very efficient. We're not doing that yet, but we're seriously considering it. I've mentioned already that we are piloting it. We already have a simplified UI, which significantly helps us in terms of markup. Because it's much easier for experts now to pronounce their verdict. We automatically collect those verdicts, and then we can quickly analyze it. Now, this way, we are able to create a new data set, improve our validations. Now, we actually have those more complex samples now that can be aggregated. This way, we can expand our existing data set. And I think that this is a great option. Also, please note that everything we've just discussed here is effectively the first stage to the development of universal embeddings that in the future are going to be transferred to much bigger tasks. I believe the first steps here are pretty optimistic, pretty promising, even if I say so myself. So, in conclusion, let me stress the following. People now often forget about the classic algos, given the hype around LLM. But remember that you can actually combine classic algos with the LMs. For example, if you don't have the markup, if you have little data, and you have a heavy algo, you can actually combine it with an LLM and have much better results compared to using the LM alone. Also, if you use, say, text-based encoders, and you cannot really consult a specific benchmark or a specific domain, it is a good idea to come up with, at least some benchmarks. Because otherwise, you can easily spend months trying to come up with the result you would easily have gotten by simply going for a different model. So optimization with a hybrid metric-based optimizations and hybrid frameworks are also something to consider. Thank you very much. This is it for my presentation. I'm happy to take your questions. Yes, thank you very much, Gleb.
Ты упомянул, что было всего лишь 106 цепочек для валидации.
You have mentioned that you only had 106 chains for validation. Have you been concerned about representativeness of that?
Не было ли идей как-то аугментировать?
Have you already thought about augmenting them by maybe adding more vertices or splitting the graphs? That's a very good question. Thank you very much. This is something we've been asking ourselves the whole way. Because indeed, that's a constraint of the system that we have. And all the decisions we're making are based on this result. And we certainly want the system to be representative. That's why along the way we took a set of measures, a bunch of measures, that were designed to help us check if it's indeed valid. So we analyzed various stats of the data set, wanted the data chains to be different in terms of size, in terms of their content. Actually, something that we discovered pretty early was that the initial data set was very easy to split by trivial features, such as chain size, for example. Like 100 versus 10 sources. So the initial data set was very easy to unbundle this way. So we realized that, such a trivial feature could easily introduce a bias in our results. So we addressed that by actually introducing more variability, more diversity in size. And we've been doing other things because we wanted to make sure that we are effectively on a plateau where we can trust our metrics. You've already told us about features that seem to be splitting the data set in a pretty robust way, but at the same time, apparently they cannot be used in the final solution. Do you have examples of other features that to a cybersecurity expert would sound like a good thing to use, but you, being an ML person, would realize that they would result in overfitting? I think that these features can actually be used in certain scenarios. It's just that in our particular case, if, say, we are developing a complex solution that generates X metrics, and you can easily forego it all by saying, okay, if it's below, between 100 and 10, do this. So I'm not just trying to say you shouldn't be using these features. I'm just saying that if you're using them, you need to be aware of the constraints. What else could be used there? Or shouldn't be used there? I actually cannot think of anything like this off the top of my head. So rather than engineering any role-based features, because it was a really very short stage, we didn't do much there. So I cannot really put my finger in any feature like this, because we opted for a universal representation right away. Okay, let's entertain questions from the floor. I'm an ML engineer named Ilya. A question about chains. Now, since you're using embeddings, it sounds like you are vulnerable to a dilution kind of attack. So with more resources, like alleged resources added to the list. Yeah, I see what you mean. This is something we have been considering from the very beginning. And I cannot tell you that the solution we have found is ideal. Let me see if I can provide a visual illustration. Apparently, it will take too long to find it. So the gist of it is like this. If we get embedding through aggregation of all the, transient embeddings, so for example, we can just go for the average embedding. Now, in this case, the concern you've raised is really serious because, you can easily, by using averages, you can have a significant dilution effect. Now, let's imagine that we have a very long chain and another very long chain like this, which contains a malicious file, like we know it from the hash. So that's a very important feature, obviously. Now, if we average it out, we can easily lose track of it. That would be a shame. In this respect, we absolutely loved this idea of matching all resources to each other, because at this stage, we do not discard anything, because there is no averaging happening at this stage. We can skip a particular resource. Like imagine that we have a chain of 2 and a chain of 10. Now the matching of them will be 2 by 2. And the rest, obviously, is kind of discarded. So this way, we can lose track of some important resources. At the search stage, it can actually distort the situation, but at the stage of getting the final embedding, well, at least we hope that by adding the algorithms that do the calculations before the averaging happens under the hood, we hope we'll be able to sort of compensate for that. But you know what? We we need to run some more exhaustive experiments to prove that. But yes, we are aware of this potential issue, and we are trying to address that. So you're effectively saying that you want to have a pipeline with simpler models and then, work with embeddings as well. Do you think that a system like this can actually be run in runtime? Yeah, absolutely. So for this product in particular, the stream is relatively sparse. It's a meta product. It actually runs on the alarms of other products. So first, lots and lots of events go to CM, and then a subset of what CM considers important goes to our system. Meaning that in our infrastructure, it is not a huge load. So the pipeline I've described is not the fastest in the world, but given the load that we have, it can be considered runtime. It can work on the fly. I guess the slowest bit is the textual encoder. The graph model is super lightweight in terms of computation, in terms of size, and if we go for this fine-grained search, well, there will be some time overhead, so to speak. But they are not colossal. Given the volume of data we have in our infra, it's not an issue, really.
Спасибо. Следующий вопрос.
Thank you. Next question.
Да, Глеб, спасибо большое. Окружной горсбер.
Yes, thank you, Gleb. I'm from Sber. Thank you very much. A very interesting presentation. We actually did something similar. I've got the following question, and one is about vector size 768, and the reason for that is the initial encoder we use. Okay, my second question then. When you initially told us about edge embeddings and how you build your graph in the first place, I was wondering whether you take into account that the time distance between events may be an important factor, like event intensity. And have you also factored in the kind of sequence of events, particularly events happening on different nodes? Yeah, that's another great question. Thank you. Now, the graph I've described is in fact dynamic. So the sequence I initially showed, it actually gets built like this in the interface. So with a new event, it's being built. In other words, time is being reflected. So far, we have not been properly taking into account. This is something we are aware of, but truth be told, we have not done much about it. So we are currently using this dynamic graph through, static snapshots, so to speak. As we are building the graph, obviously, it is dimensional. So we are showing that asset 1 generates a link to asset 2. Which means that, these are directed vectors. But we're not really accounting for the time distance. Okay, have you considered using, say, time series, where every slot would be a state or a subgraph of your graph? No, we have not done that. It's actually part of our scope. It is not a top priority, but yes, we do want to have that. It's just that, we felt it would be, pretty challenging. That's why, it's still in the pipeline, in the backlog. Effectively, we want every classification, every verdict to, happen very early so that we have time to respond to an attack being mounted. So time is obviously a very important consideration. But we have not done much so far.
Для зрителей, которые пришли после
For those who have just joined us, we want to repeat that if you want to ask your question, you need to approach the mics. And we've got 2 mics in this pretty dark room. Hello, thank you very much for your presentation. My name is Alexander, and my question is like this. Now, the features or the attributes that you used, have you considered augmented data as potential features? For example, file hosts.
Может выступать к какой системе, продукту
Can it be, say, affiliation of a particular product system, for example?
Продукт работает по какой логике
Okay.
сам по себе? Он получает...
Let me explain the logic of the product. So the product gets correlations, breaks them down by resources or assets, and one of the sub-processes is augmentation, where it grabs data from other systems. So all the information he has collected goes into the resource card. It has like 10 different fields with different attributes. At the current stage, we are only using the fields that have been sort of pre-populated by the product. So the stuff that comes from the CM system and the stuff that we get through augmentation. So these are effectively not vertices of your graph. They, in fact, are vertices. So we have those 10 fields, like I said, with different attributes.
Спасибо. И еще
So they form the vertices.
качество
Okay.
данных.
And what about the quality of input data? How much does it impact? Like the different host name formats, will that be an issue?
Этот аспект, мне кажется, тут максимально порешался как раз вот удачным выбором.
I think it has been pretty much resolved through a proper selection of the encoder. As we were shopping for the right encoder, we kind of filtered for that.
Еще как-то и так далее. То есть мы как раз...
There are different names of calling your hosts, capitalized and non-capitalized, and we wanted to make sure that, you know, semantically it would not be an issue. So as we selected the right encoder, we were able to avoid such a trap. So diversity of types here is not an issue. Now, if you are referring to, you know, broader kind of variability, we still have a kind of a bias built into our system. The infrastructure that we have is relatively large, but obviously other companies will have, you know, other content, so to speak, in their chains. That should not be a problem in the future because we do unsupervised learning in any case. So in a different infrastructure, we will be able to collect, you know, newfangled knowledge, so to speak.
Вопрос на интерес, сколько по времени обучения занимало?
Okay. And was learning fast? It was quite fast because we are using pre-made encoder. We chose not to fine-tune it. And the graph models are usually relatively small, or very small, in fact. So the main part that is we are actually, I'm sorry, training here is like training 15 or 20 minutes to train.
Благодарю.
Thank you.
Так, еще есть вопросы?
Other questions, if any? Yes, hello. I'm Evgeny from Solar. My question is not so much about the chains you're building, but rather about the system and interaction with it. So it sounds like when you're running it in a production system, even a good model will end up generating lots and lots of anomalies. So, how do you plan not to be drowned in that? What kind of tools do you provide to your users so that they can provide you with feedback and thus upgrade your system? This is exactly what we are focusing on right now. Now, the product currently is running on heuristics, correlations, and expert rules, which does generate some false alarms. So our hypothesis is that with ML algorithms, we will be able to minimize false positives, and the remaining ones we can still rank so that we can optimize the time spent by humans. So in the future, we want to make sure that we do minimize the number of FPs.
Сейчас здесь объемы, в нашей инфраструктуре это там до сотен цепочек.
In our infrastructure, we're looking at like 100 chains or fewer per day. So compared to a CM system, because, you know, we have a meta product, so we are working with a significantly smaller flow, so to speak. Okay, thank you. Thank you.
Так, ну, раз вопросов нет, вопрос задам я. Глеб,
Okay, let me ask you a question. Are the experts happy with what you have done? Well, I certainly hope so.
Мне кажется, эксперты в полной мере
It's just that, it's been close to the start of PH days, so I don't think they've really had the time to properly test it. But I do hope that after the conference, they will come back to me with, happy reviews. But even if they come bringing, negative feedback, that will be even better for the project, because it will help us improve it faster. Thank you very much, Gleb. Let's give a round of applause to Gleb. Now, the next presentation will start in 5 minutes.
Да, Глеб, мы забыли.
All right, Gleb, I'm sorry, you gotta choose the best question. Oh, right, I'm sorry about that.
Один из первых задавал вопрос про данные.
So it was one of the first questions about data. Who was that? I'm sorry, I don't see you. Well, you can remind us what the question was about. It was about the issues in the data set.
Как мы с этим справлялись? Вот один из ребят, одним из первых, с длинными...
That was one of the first gentlemen to ask a question with long hair. At least I think he had long hair. Okay.